Hello, welcome to the first video lecture of second semester, General Physics. We are starting with the topic of oscillations and waves. So this is chapter 15 in night. So we'll just talk about oscillations in general. A particular type of oscillation that's very well studied in physics because it applies to lots of different situations is when the oscillations are sinusoidal. And that's called simple harmonic motion. And then we'll look at analyzing the energy of the simple harmonic oscillator. And then the main example of this is a mass oscillating on a spring. It's the most common example. But a simple pendulum that has a small displacement also undergoes simple harmonic motion. Okay, so just to start with the basics, oscillatory motion is anything that's happening on a predictable, repeated motion that occurs around an equilibrium position. So it could be somebody on a swing. A position, if it's sinusoidal, position versus time would look something like this. And like I said, a mass on a spring is a good example of that. So just to kind of review some definitions, when we talk about oscillations, the period is the time to complete one cycle. So on this graph, right, from maximum down to minimum, back up to maximum, again, will be a period. If you're on a swing, it's, you start at the maximum height, go through the equilibrium position at the bottom, back up to max height, and then come back to the starting point. That is your period. Frequency is another way to characterize the rate of the oscillation as well. And so it's measured in units of hertz. It's the number of cycles. Again, how many complete cycle, top to bottom to top, it would undergo in a second. And so these are inverse relationships. The frequency is 1 over the period, or the period is 1 over the frequency. And just to remember that hertz, right, is 1 cycle per second, sometimes just written as per second. Okay, so like I said, the most common type of simple harmonic oscillator is the mass on a spring. So here I'm just using the PhET simulation from the University of Colorado, which is great. So we can put different masses on a spring. So I just hung a mass here. It's stretched out the spring to a certain distance, and this green line is showing us what we call the equilibrium position, right? With no motion, this is where the weight of the spring is balancing with the upward force. Sorry, the weight of the mass is balancing with the upward force of the spring. So remember, we'll talk about it in a second. Remember, we analyzed last semester the force exerted by a spring depends, it scales linearly with how much you stretch the spring. It's called Hooke's law. So if I pull this mass down a little bit and let it go, we'll see that it actually just oscillates up and down and up and down. And again, we follow sort of the connection point and looked at how that was moving with time. It's down, up, down, and up. Let's see if I can do it with my pointer's gone. And again, if you graph that out, not just me trying to sketch it on the screen here, you would see sinusoidal motion versus time. Okay, so important positions to think about, when it's at its maximum displacement here, right, when the mass gets down to the end of wherever it's going to travel, at that particular point, it's turning around, right? So it's moving down, it actually stops momentarily, turns around back toward the equilibrium position. So either at the minimum or the max of its position, its velocity at that instant is 0, okay? And then as it passes through the equilibrium position, there's actually no potential energy stored in the spring at that point, let's say, compared to how it is at equilibrium. Right, so you get sort of maximum potential energy either at the max or min height, and then max kinetic energy, the energy of motion as it passes through the equilibrium. Okay, so that's nice. That's available for you if you want to play with that, try different masses, all that kind of stuff. So again, this is an image of a mass oscillating horizontally, like on an air track, so something frictionless. It's attached to a spring here, and it will oscillate back and forth. So this is showing you the position of the cart as a function of time. And so it goes out to the equilibrium, or the maximum extent of its motion. It stops, comes back through the equilibrium, back out to the other side, stops and turns around, and will just keep oscillating back and forth. And if there was no friction, this motion would go on forever. Okay, so the maximum displacements away from, so we always say 0 is the equilibrium position. The maximum displacement away from that equilibrium position, you can see here it's labeled A, that's called the amplitude of the motion. okay? All right, so we can use our knowledge from last semester about forces, and if you need a refresher, we posted kind of a quick phys 130 review video that you can watch for just a quick review on forces and energy. Okay, so if we look at the forces acting on, again, we're going to say this is a frictionless surface here. Frictionless surface that this mass is sitting on. This is the equilibrium position. So we've pulled it out a little bit to the right, and then we're going to let it go. And like we just saw in the simulation, it's going to oscillate back and forth about the equilibrium position. So at this particular point, if we're just looking at the forces in the horizontal direction, there's a force, basically only the force of the spring, because we're ignoring friction, is going to be directing it back down toward the equilibrium position. Okay, so let's analyze that motion at that particular point. So we're not all the way out at the max amplitude, we're just at some in-between position x. So if we sum the forces in the x direction, right, this is our one of the most important relationships we did last semester, F equals ma. So again, those are vectors. If we just look in the x direction, say the sum of the forces in the x direction is mass of the block times its acceleration. And we know from the free body diagram that it's the spring that's providing the force in the horizontal direction. And we also know that the spring force scales with how much you're stretching it by Hooke's law, right? So we have negative kx, that's our Hooke's law, is equal to mass times acceleration. And if we, oops, where are we going? Sorry. If we just solve for the acceleration, we get that it equals negative k, that's the spring constant k divided by the mass times x. And we're just going to make a couple of substitutions here. We're going to say that omega squared, so remember omega is the angular frequency. It's related to the other frequency just with a factor of 2 pi, because omega is in terms of radians per second, frequency f is in cycles per second, and there's 2 pi radians per cycle. So we're going to say omega is the k over m, or omega squared is k over m. And then just using our derivatives, right, we know acceleration is the second derivative of position versus time. So if we rewrite this equation, instead of acceleration, we're going to say d squared x dt squared is minus omega squared times x. Okay, so this is what we call the equation of motion, meaning that it's telling us how the object accelerates versus time. That's the equation of motion, okay? So it's equal to some constant, right? K and m are just constants, times an equation that tells us our position versus time. Okay, so we'll look at this a little bit more in the next slide. But so just things to note, right? The acceleration is not constant. Acceleration depends on the position of the mass, where it is along this part, right? So when it's at 0, the acceleration is 0, right? It feels no force in the spring. When we're at our maximum displacement, we get our maximum acceleration. In general, that differential equation is one of the most important equations in physics. Okay, so this is a differential equation. I realize a lot of you haven't had differential equations yet, so I'm going to give you my quick overview of differential equations, which means how we solve them is we make guesses, right? So we just need to understand what this equation means in words, right? So it's saying I have some function x, I take the derivative, and then I take the derivative again, right, to get the second derivative, and I get back my original function x, some constant out in front, and a minus sign. Okay, so I'm going to take some function, I take the derivative once, take the derivative again, and I get my function back with some numbers out in front. Okay, so the functions that should come to mind that would satisfy this are sine and cosine. We could also use the exponential function too, but we're just going to focus on sine and cosine. Okay, so let's look at this, just walk through kind of a refresh of Calc 1, right? So if I say my function is sine of x and I take the first derivative of that, I get cosine of x. And if I take the derivative of that, so the second derivative of f of x, I get derivative of cosine is negative sine. So I've gotten back my original function sine times the negative. And cosine works for that as well, right? So I have, if I say f of x is cosine x and I take the derivative of that, I get negative sine. And if I take the derivative again of that, I get back the derivative of sine is just cosine. I carry through that negative sign and I get negative cosine. Okay, so the way we are solving, in quotation marks, this differential equation is we're going to say, let's just try an equation that looks like this. So I'm going to give it some constant out in front and a cosine and something times t. That's our angular frequency omega. Okay, so let's switch quick to our camera and go through that. Okay, so remember our differential equation says the second derivative of x with respect to t. Let's see if we can zoom in a little bit there. Okay, equals some constant, right, minus omega squared times x. That's what we got from our just analyzing the force of mass on a spring. Okay, so now I'm going to say, I'm going to test and see if this function works. Okay, so let's just review our derivatives here. So if I want to do dx dt, I have to take the derivative of this function. So a is just a constant, so that stays there. Derivative of cosine is negative sine. I'll just first rewrite what's inside that argument, right? And then afterwards, I have to take the derivative of what's inside there with respect to t. So the derivative of omega t with respect to t, the t just becomes 1, and we get a factor of omega out there. So if I bring my constants out to the front, I get minus omega a sine omega t. Okay, and that's my first derivative. Okay, and then I'll take the second derivative, d squared x dt squared. So now I'm taking the derivative of this function with respect to time. Again, these are constants, so I'm going to just bring those down. And, okay, and now I need to take the derivative of sine omega t with respect to t. So derivative of sine is cosine omega t. And then again, I need to take the derivative of what's inside there. So derivative of omega t with respect to t, since omega is just a constant, we'll just get another factor of omega. That makes that a little easier, huh? Okay, so hold on, there we go. Okay, so now we can combine our omega functions, right? So we have d squared x dt squared is minus omega squared a cosine omega t. Okay, and if we look back up, that's what we started with, right? This is x. So in fact, this function, a cosine omega t, does satisfy this differential equation that says I take two derivatives of the same function, I get back a minus sign, I get back a constant squared, and I get back my original function x. Okay, so x equals a cosine omega t. That works. Okay, and that's our crash course in differential equations. Okay, don't tell any math people about that. Obviously, there's a lot more involved just than guessing, but that's how I think about it. Okay, so we're going to add another extra little, now that I just told you that that works, we're going to add another little extra constant in here, which is called the phase constant. So for this graph, for example, right, we're starting right at t equals 0, we're starting at our maximum displacement. Sometimes that doesn't happen, and your sine or cosine curve gets shifted a little bit left or right, and so this phase constant allows you to shift it in order to meet whatever the initial conditions are. So just to refresh, so the quantities in this equation, A is the amplitude, and that is the maximum displacement, right? So in this case, it would be 0.1 meters. Omega is the angular frequency, so that is 2 pi over the period, right? So I could measure out the period in seconds, do 2 pi divided by that, and I would get what omega is. And then the phase constant phi is in units of radians, and we need that if x is not equal to the amplitude when t equals 0. Okay, so let's do one example here. So based on this graph, we want to write what the equation of motion is. So let's exit full screen here and get our camera back. See if we can get these guys side by side. Here we go. Okay. So let's write down some of the things that we know based on the graph. Okay. So I'm just reading off the graph. So it looks like a negative cosine graph. Okay. So this is where y equals 0, x equals 0, whatever. X equals 0, we'll say. And then from the graph, it's not the best numbering, but this is -5, and that's 5. And it says it's in meters, which is quite a large wave. Okay, and then from the graph, we can also read up. So it starts at the minimum. When does it get back to the minimum again? Because that's going to be one period, the period t. And from the graph, it looks like that happens at 2 seconds. Okay, so things that we know then that were given from the graph, we know that our amplitude is 5 meters. We know the period is 2 seconds. Okay, and now we want to fill out the rest of this equation that x equals a cosine omega t plus phi. Okay, so we said that there's this connection between the period and omega. So omega equals 2 pi divided by the period. So 2 pi divided by 2 seconds equals pi. And then our units are radians per second, so that's good. So now we can rewrite our equation, right? That x as a function of time is our amplitude, 5 meters, times cosine omega, which is pi radians per second, times t plus phi. So we are almost there. The thing that we don't know yet is phi. And the way that you usually solve for what phi is that we set t equal to 0. So we're going to set t equal to 0 and then solve for phi. Okay, so we're going to say x, if t equals 0, x equals -5. And then on the right side, we'd have 5 meters. That's our amplitude. We have cosine pi radians per second times t, but now t equals 0, right? So this whole thing goes to 0. And then we still have plus phi in there. Okay, so we can divide both sides by 5 meters, so we get -1 equals cosine, and the omega t went away, that's 0, right? So cosine of phi. So now we just take our inverse cosine of both sides. Arc cosine on both sides over here too. And so I get phi, just swapping sides, is going to be arc cosine of -1, right? Or inverse cosine of -1. Those are equivalent. The angle whose cosine is -1. That would be pi, right? Yeah, so I calculated it before, but we even know just from our, like if we sketch out a regular cosine curve. We start at 1, we go down to 0, or -1, 0, and then back up. And this, where it hits -1 for just a regular normalized cosine curve, happens at pi. So we don't even need a calculator to know that phi equals pi. Okay, so then our full equation of motion is, let's zoom down a little bit. Right, so x as a function of t will be 5 meters. It's our amplitude times cosine pi t plus pi. Knowing that this actually has radians per second as the units, but I'm just trying to streamline it a little bit. Okay, so that's that. Alrighty. Okay, so like we said, if this, the motion is not at the max amplitude at t equals 0, then you need some kind of a phi to shift this over. So the blue curve here is just showing us a regular cosine curve where phi would equal 0. The green curve is showing us a cosine curve that's been shifted by pi radians. So it looks like a minus cosine curve. Okay. And then you can think about what would it look like for pi over 2, a shift of pi over 2. Nope, spoiler alert, looks like a negative sign. Okay. So we went through this, right? I just did this out on paper, right? How we go through these derivatives. So, but we didn't talk about it really in terms of velocity as it's an in-between step, right? So velocity is a derivative of position versus time. And based on what we looked at before, right, or just taking the derivative of this again, we get negative omega times the amplitude times sine omega t plus phi. So if we start out with a cosine curve as our position versus time, our velocity looks like a negative sine curve, but it's got a slightly different amplitude, right? Instead of just a, it's omega a. So that gives us an amplitude of velocity, right? Because a is meters, omega is per second, so we get a meter per second. So this tells us about our maximum velocity is omega a. Okay, we do this again, take the derivative again to get the acceleration, and we get like a negative cosine curve, right? So acceleration looks like this, okay? And the maximum amplitude would be omega squared times the amplitude of position. Okay, so that'd be a maximum acceleration. Okay, and these are just restating that, right? So the maximum velocity would be omega a, that just comes out of the derivative. Remember, omega we defined as the square root of k over m. So for a mass on a spring, it would be k over m times the amplitude. And then for the maximum acceleration, it would be omega squared times a, just taking the absolute value, right? Again, we square omega, we get k over m times the amplitude. Again, just looking at the figures, right? So velocity is 90 degrees out of phase with position versus time, and acceleration is 180 degrees out of phase. And it's good to just stop and think about that for a while because there's a lot going on in terms of velocity, acceleration, and position when you're looking at a mass oscillating on a spring. But this inverse between position and acceleration comes from Hooke's law in our typical case. Okay. All right, so what we haven't looked at is the energy. So oftentimes energy is a useful way of analyzing the motion of a simple harmonic oscillator. And so we're looking at a mass on a spring. The other case that exhibits, common case that exhibits simple harmonic motion is the pendulum as well, which we'll look at in a sec. But so just stepping through the motion of a mass oscillating horizontally on the spring. So it's at maximum displacement. It passes through the equilibrium. It goes to its maximum compression, back to equilibrium, and on and on and on it will go. Okay, so this kind of just steps through what the different values are. So, here's time, that's advancing down as we go, and then what the position is of the mass on the spring, what the velocity is, what the acceleration is, and then also what the kinetic energy and potential energy is. So do you remember for a spring, right, or just in general, kinetic energy is 1/2 mv squared, and the energy stored in the spring is 1/2 k delta x squared, where that delta x is how much you're compressing or stretching the spring from equilibrium. So at the starting point, we are pulled out to the maximum displacement, that's our amplitude. So x equals a. The acceleration that we're going to feel is at its maximum value, so it's negative omega squared a. When we start, we're going to start it from rest at 0 kinetic energy, and all of the energy is stored in the spring potential energy, and that's equal to 1/2 ka squared. This is really important. The total energy of the spring will always be 1/2 ka squared, right? Because in this case, the total energy is just potential energy. Okay, as it passes through the equilibrium, right now we're a quarter of the way through the cycle, all of our energy is now in kinetic energy, and our potential is 0 because the spring is at its equilibrium. Okay, our velocity is at its max value there. Halfway through the period, we've gone now over here, so it's at the furthest extent on the other side. Acceleration now has flipped direction. It's going to be pushing it back to the right. You think about it in terms of forces, but in terms of our energy, we're still just total potential energy and no kinetic energy at that point, right? So it's at its turning point, it's momentarily at rest, all of the energy is potential. Again, it passes back through the equilibrium position. We're back to total kinetic energy, and for that instant, the potential is 0. And so it will just keep oscillating, right? Potential to kinetic, to potential to kinetic, as it goes from maximum extent to equilibrium, maximum extent the other side, back to equilibrium. Okay. A cool thing is that simple harmonic motion and uniform circular motion are really closely related. So this nice illustration here. So on the left, we're looking at a mass oscillating on a spring, let's say, up and down. And this could be plotting kind of the phase of its motion, or the whatever, the y-axis as a function of time. And this is actually really kind of the phase, I guess, of its motion, you say. And then this is showing you the height of it versus time. So simple harmonic motion, right? If we look at the position versus time, it's a sine curve or cosine curve, depending on where you start. But this is uniform circular motion, right? So you can think of simple harmonic motion as just this projection, this 1D projection of circular motion. So there's a lot going on here. I encourage you to look at this link and just kind of look at how everything is fitting together here, right? Because it's a lot of detail. Okay, so let's, we're almost done here. Let's look at the pendulum as another example of simple harmonic motion. So this only works for small angles, and we'll look at why that is in a sec. But if we look at a pendulum that's displaced a small amount from equilibrium, right, the forces that are acting on it are the tension of the string pulling back toward the wherever it's pivoting about, and then there's the force of gravity acting downward. Okay, but because it's kind of confined on this by the string, it actually can't move, horizontally this way. It's going to always move kind of tangent to the string, not spring. Sorry. Okay. So the force of gravity is directed downward. And if we look at the displacement angle, right, this is one straight line here. So the force of gravity with, let's say, the radial component of gravity is the same angle as the vertical with the string. So that theta and that theta are the same. So there's a component of the gravity in the radial direction, and then there would be another component here, which is shown with this arrow here, in the tangent direction, right? So tangent to the string. And that's what's going to cause the motion. Okay? So it is the opposite side of theta, right? So it would be mg sine theta is this tangent component. So that's what's shown right there. Okay, again, we can go through our force analysis, and we're just going to look at the forces in the tangent direction. So in the radial direction, the tension in the string will always balance the radial component of gravity. So that just goes to 0. In the tangent direction, we have unbalanced force, so we get acceleration. So if we sum the forces in the tangent direction, we have negative mg sine theta, right? Because that would be a positive angle. That's pointing back the other way, and that's going to produce acceleration in the tangent direction. So again, we can do this acceleration in the tangent direction as the second derivative of position, and so our equation becomes, this is our acceleration, d squared theta dt squared, and we get minus g over L times sine theta, and this is already getting long, so we're not going to work through the details of that. But what we also do, and this is why it only works for small angles, we have to be able to use this approximation that sine theta is approximately equal to theta. This is true, right, when we're in units of radians. And when we get that, then we get the second derivative of theta is some constant, right, and a negative sign times theta. And so that we need to start recognizing as a differential equation that is telling us that this object is undergoing simple harmonic motion. Okay, if we do the same analogy saying that this constant out in front has to be omega squared, then omega in this case is the square root of g over L. Okay, and that can actually lead us to calculate the period of the pendulum and all that. Okay, So we talked about energy a little bit, right? So the total energy of a harmonic oscillator, right, mechanical energy of any system is kinetic plus potential. But when we're talking about a mass on a spring, it's 1/2 mv squared plus 1/2 kx squared. And then again, when we're at the maximum displacement, when x equals a, our kinetic energy is 0, and our total energy would be 1/2 ka squared. So that's a nice relationship that is always true, right? The total energy of the mass on the spring is 1/2 ka squared. Okay, so we'll finish up with this example. So we have a cart that's attached to spring, and it's going horizontally. And let's just write some stuff down. So we know that the mass of the cart is 2 kilograms. It's horizontally attached to a spring with spring constant 15 newtons per meter. The system is set in motion when the cart is 0.24 meters from the equilibrium. So x0 is 0.24 meters. And then it's also given an initial velocity at that point with 2 meters per second away from the equilibrium position. And then we need to find the amplitude and then velocity at x equals 0. Okay. So let's switch over to Ladybug. Go full screen mode here. Okay, so remember we're going to set up our problems here so that we get our full presentation points, right? So I already wrote what we were given based on reading the problem, what we need to find, and then we're going to draw a nice picture, right? So we have a concept in our head of, let's say, a mass on a spring, and then let's say this is our equilibrium position. Okay, and then initially it's pulled out a little bit further. So this is t equals 0. And so it's given some initial displacement that was 0.24 meters. And you notice that that's our x0. And it's given a velocity in this direction. Okay. And then some later point, right, it's going to go out to its maximum displacement here where its velocity will be 0. And then its position will be equal to the amplitude. And then even sometime later, right, it'll come back in and pass the equilibrium going this way. X equals 0, and we have some velocity going this way, which would be its max velocity. Okay, so we want to find A. That was the first thing, find A. And I'm going to use energy analysis. So if I look at, let's just call this position A, position B, and position C, because we're going to want to analyze all of those to get our velocity at x equals 0 too. And let's do our bar charts. So make some energy bar charts. So at position A, so for this, we're always going to have kinetic and potential in the spring. Okay, and we have some mix at position A, right? Because it's stretched out from the equilibrium and it's moving. So it does have some potential. And it does have some kinetic because it's moving. I don't know how they're situated relative to each other, but let's say it's about the same, okay? And then at position B, we've gone all the way out to our maximum displacement. Our velocity is going to be equal to 0 right there. So my kinetic energy is going to be 0 at position B. And in a little bit, I'm going to have all potential energy in the spring. Okay, and then at C, we're going to come back through the equilibrium. This is how we'll find our velocity. So at that point, my displacement is 0. Right, so my energy in the spring, right, is 1/2 kx squared, and my kinetic energy is 1/2 mv squared. Okay, so when I come back through position C, x equals 0, and my potential energy is 0, and so all of that energy will be in kinetic. Okay, so it kind of shows us how we can solve this problem, right? So the first one is to solve for amplitude, and here, in fact, our potential energy is 1/2 k a squared, right? Because we're at position A at that point. And then here, when we get back through the equilibrium, this is going to be 1/2 mv squared. Okay, so we can use the information we get about the initial position to figure out what the total energy is, and then use that to solve for A, right, at position B, and then also the max velocity at position C. So let's compare A and B. So we get conservation of energy says, let's start general, right? Kinetic plus potential at A is going to be equal to kinetic plus potential at B. So we have 1/2 mv squared plus 1/2 kx squared equals 1/2 mv squared plus 1/2 k a squared. Okay, and this velocity at the maximum displacement is 0. Okay, and we want to solve for that. That's our unknown. So everything's got a half. All these terms have a half, so we can get rid of that. So we have mv squared, and let's divide both sides by k as well. So we'll divide all the way through by, 1/2 k. Okay, so on this side, we're just left with a squared. On this side, we have 1/2 mv squared divided by 1/2 k, so we get m over k, b squared, 1/2 k to 1/2 k, so on that, we're just left with an x squared. And then we want to take the square root, and I'm going to flip sides on you. So we get m over k, b squared plus x squared. And now if we plug in our values, we have our mass is 2 kilograms, our k is 50 newtons per meter, our velocity was 2 meters per second, and square that, and our position is 0.24 meters. Okay, so let's look for okay, so we got square root oops, 2 divided by 50 times 2 squared is 4 plus 0.24 squared. So we get an amplitude of 0.47 or 0.466 meters. Okay, and then we have to find our velocity, which again, we're just going to say is, we can use the same relationship, right? 1/2 ka squared equals 1/2 mv squared. Doesn't matter what points we set equal to each other. So this is at position B, right? And this is at C. That's our energy, what our energy would simplify to. So our amplitude we just said was 0.466. So let's solve for V first, right? So we have a half on both sides, so we can just divide through by M. And we get, again, I'm going to swap sides here. So V squared is K over M, A squared. Let's take the square root of both sides. And we get V equals the square root of K over M times the amplitude. So K was 50 newtons per meter. Our mass was 2 kilograms. And then our amplitude, we said, was 0.466 meters. So 50 divided by 2 is 25. And then we take the square root of that, that's 5. And then what are our units? So we have a Newton, I'll do that over here. So a Newton divided by a meter divided by a kilogram. So a Newton, remember, is a kilogram meter per second squared. We're dividing by a meter and divided by a kilogram, so we get a 1 over second squared. So those go away. And then we took the square root of it. So it's 5 times 1 over second. And then 0.466 meters. So let's just call that a half. 5 times a half is 2.5 about meters per second. Phew. All right, and let's call that done.